Welcome to day one of the 30 days of Earth and Space Sciences. Today, we're going to talk about what makes Earth's surface habitable. And I'm going to give you more of a geological background to all of this. And please remember to subscribe. I'll be part of our 30-day journey in Earth and Space Sciences. And also visit creo.space for more information about our programming and for other ways to gain knowledge about Earth and space sciences. There it is. Let's begin with the concept of convection. Convection is something that you are quite familiar with. Frequently, we look at examples such as boiling water. So when the base is heated, water rises because it's less dense. It cools at the top and falls to the side. Air does this too. It's a classic physical property of fluids. And shown here, cool air sinks here in this left diagram with the blue arrow going down, and warm air rises. Notice that that is at land surface over here during the day. The land surface is warmed by the sun. It warms the air above it because of infrared radiation from the surface to the air. That air rises. It cools by expansion because as air rises, the air pressure decreases. Air expands. And if you expand a gas, you cool the gas, and so then it falls. In the nighttime, this process can be reversed. The surface temperature of land can cool quite a lot faster than, say, an ocean surface. Ocean water has an enormous heat capacity, so that winds actually can change direction, of course, from daytime to nighttime on your coastlines. And also shown here are some animations showing airflow associated with convection. Convection is a very important concept in geology. Earth's climate is regulated by geology, and that regulation is called the CO2 cycle or the carbon dioxide cycle. CO2 is a greenhouse gas. So the amount of CO2 in the atmosphere affects long-term climate. Carbon dioxide is carbon with two oxygens, and this carbon dioxide, of course, has a shape sort of like a dumbbell, and it has a lot of vibrational frequencies. So basically, it, as a gas, vibrates thanks to infrared light that is radiated off of a warm surface like a land surface. That's how CO2 acts like a greenhouse gas. CO2 can dissolve in water. It dissolves in the oceans. When it does so, it can combine with eroded silicate minerals to form carbonate rock. And that's the way our Earth captures carbon dioxide from the atmosphere by weathering reactions and puts it in the ocean. And that's shown in this cartoon here on the right, where carbon dioxide in the atmosphere comes out of ultimately volcanoes or any kind of degassing, or from industrial processes. Burning puts CO2 in the atmosphere. That CO2 can dissolve in the ocean, and rainfall erodes silicate minerals on land. All of this going into bodies of water where silicate minerals react with dissolved carbon dioxide as bicarbonate to form carbonate rocks. Ultimately, these carbonate rocks, limestones and their kin, can be subducted and recycled back into the Earth's mantle to eventually be released again over geologic time by volcanism. Plate tectonics, which is the motion of Earth's crust as plates, discrete segments of crust that interact with one another, leads to subduction, which is a recycling mechanism for plates, melting, and volcanism. This releases carbon dioxide back to the atmosphere. Burial of organic matter from life forms, plants and animals, regulates oxygen and carbon dioxide in the atmosphere, because organic matter removes also carbon dioxide from the atmosphere, traps that carbon as living matter, which can then be buried as dead matter. Oxygen, if it is in contact with that dead organic matter, can oxidize it back to CO2 in the atmosphere. Or that organic matter can be burnt, as we do with petroleum. So oxygen levels will rise if you increase the rate of burial of organic matter. Oxygen levels will go down if you decrease the rate of burial of organic matter. And that has to do with oxidation. And what are some other greenhouse gases that you know besides carbon dioxide? Turns out water vapor is a really great greenhouse gas. It has a short residence time in the atmosphere, meaning it rains out. Another really strong greenhouse gas is methane. Methane, which is released by organisms called methanogens, also by many higher order organisms, cattle and are a great source of methane. Industrial processes can release methane. Methane can also be released in volcanism. It's not a lot, but there's some there. There are a few other greenhouse gases, but those three are the principal ones: carbon dioxide, methane, and water vapor. And of course, ultimately, in geology and in the crust, what goes down must come up. But how and why does the crust go down and then come back? So here's a question for you to think about. Which of these is not a greenhouse gas? I mentioned some greenhouse gases. I'll give you a moment. Yes, of course. Argon is not a greenhouse gas. Argon is a noble gas. It's a gas that comes out of Earth's mantle. Can be argon-40 from the decay of potassium-40. And it is a noble gas, so its outer electron shell is completely full, so it has no chemical reactivity. Water vapor, carbon dioxide, methane, nitrous oxide, sulfur dioxide, all of these different gases are greenhouse gases, but noble gases like argon and helium and neon, etc., are not. So, plate tectonics and recycling. The plates move. We've mapped the movement of the plates using paleomagnetic directions. We know the evolution of the plates and the evolution of landforms for the past billion years or so. And we know that these plates move relative to one another, either at divergent zones, like here in the mid-ocean ridges on this map on the lower left, convergence zones, like here in this map where you have subduction taking place or collisions, and also transverse movements, so major slip fault regions of the crust. So plate tectonics. What is plate tectonics? Well, as I mentioned, Earth's crust is divided into plates. New seafloor crust, made of a rock called basalt, is made by spreading at mid-ocean ridges, these divergent zones that I mentioned. So these mid-ocean ridges make mid-ocean ridge basalt. And that's shown at the lower left here in this diagram. Old oceanic crust descends and melts at subduction zones. I mean, the average age of oceanic crust is about 70 million years. The oldest oceanic crust is around 200 million years in the northwestern Pacific. But the average age of the continents is 2.5 billion years. That's because continental crust, which is thick and granitic and very buoyant, is extremely difficult to subduct. You can only get rid of it really by eroding it and putting it down subduction zones as sediments. In any case, melted magma rises up to form volcanoes of lower density, sort of intermediate to highly siliceous crust called continental crust. And in processing this rock, you get granite eventually. But great examples of this process are found in the Andes or Cascades, basically this great north-south mountain range that's found in the Western Hemisphere. The Earth, as I mentioned, is divided into plates. But if you were to look at a cross-section into Earth's interior, which we are able to do using sound waves, it's called seismology, and these sound waves may be from volcanoes or volcanic eruptions, earthquakes, even nuclear bomb testing. You see that the Earth has an inner core, an outer core here, very deep down, but then most of the Earth's volume is mantle, and that mantle convex, like in my opening statement here. It's hot at the bottom. It causes that mantle rock to become less dense than its surroundings, so it rises and reaches the top of the mantle where it can cool, and then that cooling part of the mantle then sinks and sets up these convection cells. And people have mapped these convection currents in Earth's mantle, and that's shown here in this diagram. This shows that Earth's interior is dynamic. It moves very, very slowly because, of course, the Earth's mantle is not molten. It's solid and crystalline, but it deforms plastically and slowly. So, what if we look at some animations of subduction at old fracture zones? We can do that, shown here. Here is a cross-section showing cold crust here with warm crust beneath it. And this material will eventually subduct, the cold material will subduct underneath the warm material and go into the mantle. And just to remind you, here's a map again of all of the different plate boundaries. This is the mid-Atlantic ridge system here between the western and eastern hemispheres in the center of the Atlantic Ocean. There are parts of this divergent zone, mid-ocean ridge, that reach the surface, Iceland being a spectacular example. And then the so-called ring of fire around the Pacific, areas where the margins of the Pacific Basin have oceanic crust that is subducting, and that's causing volcanism and earthquakes. So why does Earth have plate tectonics? It's the only planet in our solar system that has plate tectonics. Well, it's because our Earth's interior is hot. It's powered by leftover heat of accretion, so gravitational heat, but it's also powered by radioactive decay. And convection in this mantle drives plate tectonics. The crust is thin compared to the other terrestrial planets, Mercury, Venus, and Mars. And that's because we have water at our surface. And water allows for a thin oceanic crust. And water, some people say it lubricates the plates. Well, What it really does is it allows motion and melting of the oceanic crust, because the water penetrates the oceanic crust and mechanically weakens it. It lowers the oceanic crust melting temperature, allows the oceanic crust to deform, and that oceanic crust does something peculiar. When it deforms and it goes down at its margins, or its subduction zones, as it goes down and temperature and pressure increase, that oceanic crust undergoes a transformation. It becomes eclogite. So it transforms from basalt to eclogite or garnet eclogite. So it transforms from basalt and hydrothermally altered basalt, which is of relatively low density, to eclogite, which is more dense than the surrounding mantle, which causes that plate to sink. So it's slab pull plus the chemical alteration, the oceanic crust, and convective currents at the mantle that drive plate tectonics. So heating from below, as I mentioned, causes convection. So one can model that numerically, like what's shown here, where you have a heated base, like at the core mantle boundary of the Earth, and that causes plumes of cooler material to rise, or hot material to rise, excuse me. Then it reaches the base of the crust where it can conductively cool or cool by volcanism or by plate spreading motions. And then that mantle parcel can sink. So that's why Earth has plate tectonics and the other planets do not, because we have the internal heat, thin crust, a lot of convection, mechanically unstable oceanic crust, thanks to lots and lots of water at the surface. Here's another view of some of these convective currents. Now, this black figure here, this circle, is to represent the core mantle boundary. So we're looking at the whole mantle now in this vertical cross section. And you can see these light colored sort of hot mantle plumes coming up from that core mantle boundary. And here's another representation here of this kind of convective behavior in Earth's mantle. Thanks to water. Everything that I've told you about internal heat, crustal thickness, and so on is planet specific. The mass of Venus is pretty close to that of Earth, about 81% of Earth's mass. But Venus has no plate tectonics. It appears to be trying to have plate tectonics, but lack of water at the surface, because Venus's surface is so hot, prevents the stability of liquid water. In the absence of liquid water, you can't mechanically weaken Venus's crust. So Venus's crust is very, very stiff. It deforms by lateral lithospheric creep. It collapses on itself. And yes, of course, Venus has internal heat. It has the same gravitational heat as the Earth. And it very, very likely has the same internal radioactive production of heat as the Earth. But it can't have plate tectonics because there's no liquid water at the surface. Earth, interestingly, is called Earth. Arthur C. Clarke once said, "Isn't it curious that we call our planet Earth when it should so obviously be called ocean?" Here's a view centered almost about over Hawaii, showing Earth as a water world, mostly bereft of landmass from this perspective. So we have subduction, we have mid-ocean ridge areas. These are also places which besides the fact that Earth loses heat there, there's a great deal of volcanism and a lot of chemistry. You may have heard of these deep hydrothermal vent areas. These are associated in the oceans, mostly with divergent regions, areas where the plates are spreading apart, but not exclusively. They can be associated with hot spots, areas where volcanoes are punching through the crust. So what happens, of course, is that cold ocean water seeps into the crust, here shown in this diagram on the lower right. That water going into the crust gets heated at depth into the crust. That heated water causes the dissolution of chemicals, which then erupt as hot mineral-rich water and condenses into black sulfur-rich metal chimneys at the base of the ocean. These are places which have not just very interesting chemistry, but fascinating biology. I told you that the age of Earth's crust is different for different kinds of crust. Continental crust has an average age of about 2.5 billion. The oldest continental crust is found here in the Northwest Territories of Canada, in the Casta Gneiss complex. It's about 4 billion years old. There are other places which have very old rocks. Northern Quebec has rocks that are about 3.8 billion. Same with Greenland here, the western part of the island of Greenland, 3.8 billion. Rocks from southern Africa, 3.5 billion. Rocks from Western Australia, 3.5 to the oldest components there, 3.7 billion or so. Northeastern China and some other parts of China also have very old rocks, close to 3.8 billion. But oceanic crust is much younger, average age 70 million. That's because it forms and gets effectively recycled. The oldest is, as I mentioned, here in the Northwest Pacific. What about the effects of subduction? Well, one of the big ones, of course, is earthquakes. And earthquake happens near a fault in an oceanic environment, you can make a tsunami. That happened with the Indo-Australian plate and the Eurasian plate near the island of Sumatra not so long ago. A powerful subduction zone earthquake occurred, and a huge tsunami was formed here, which caused the Indian Ocean to ring like a bell with waves. Tsunami waves are also colloquially termed tidal waves, washing back and forth and causing tremendous devastation. This is a consequence of the rapid movement of Earth's crust and the displacement of water. Other subtle examples of the activity of Earth's crust shown here, strike slip faulting. You see these rows of trees have been offset because there's an area of active movement along a fault line in the crust. This can even be seen subsequent to earthquakes and displacement of things like railroads or fences or roadways, and unfortunately sometimes devastation, where whole cities can be demolished. That's the trace of that strike slip fault. Recall, Earth's climate is regulated by the carbon dioxide cycle. Plate tectonics releases CO2 back in the atmosphere from recycling ultimately that CO2 as organic matter and carbonate rocks into the mantle. And our Earth is habitable thanks to this plate tectonics and CO2 cycle. What heats the surface? It's not radioactive heat from the crust that keeps our surface habitable. It's the atmosphere cloaking the surface of our planet that's heated by the sun. Greenhouse gases are not bad. They're actually necessary to keep the Earth habitable. Too much of a good thing is a bad thing, but Earth is habitable because we have enough CO2 and methane in the atmosphere to trap the sun's rays to keep our climate equitable, clement for life. If there were no greenhouse gases in the atmosphere, Earth would be quite cold, probably frozen, like as a snowball Earth. This air, of course, experiences convection because the sunlight heats the land surface, and that land surface radiates back in the infrared and heats the air above it, and you have convective currents in the atmosphere. A little bit more about the greenhouse effect. The way the greenhouse effect works, of course, is that sunlight passes through the atmosphere, visible light passes through the atmosphere. It strikes the ground. Some of that is absorbed, that energy is absorbed, heating the ground. It re-radiates in infrared light to the air above it. And if that air has lots of greenhouse gas in it, the greenhouse gas absorbs the energy of that infrared light and re-radiates it as heat. So some of that infrared is trapped by greenhouse gases in the planet's atmosphere. It causes the lower atmosphere, where it's denser, to heat up, and thus the surface to heat up. The surface is hotter than if we had no greenhouse effect on the Earth. So the chief greenhouse gases are water vapor, carbon dioxide, and methane. In a balanced system, the Earth regulates the carbon dioxide in its atmosphere by a balance of weathering, denudation, erosion, and dissolution. The oceans dissolve carbon dioxide. Plate tectonics releases carbon dioxide. Over geologic time, this has kept Earth's climate relatively stable. If it's too cold, there's less chemical weathering from the carbon dioxide dissolved in water, and less CO2 loss. So more builds up in the atmosphere, leading to more greenhouse warming, and then the system rebalances itself. If it's too warm, less carbon dioxide can dissolve in warmer ocean water. So less builds up in the atmosphere, and you have less greenhouse warming. It takes about 400,000 years for the carbon dioxide cycle to restore balance if it's thrown off. So Earth has a kind of thermostat. So too warm, oceans dissolve CO2, more carbonate minerals form, less CO2 builds up in the atmosphere. Weakened greenhouse causes the planet to cool down. If it's too cool, the greenhouse will warm the Earth back up because fewer carbonate minerals form, more CO2 builds up in the atmosphere. Sometimes, and this happened at least twice in Earth's history, the whole system goes off. There are episodes of greater cooling, so-called ice ages or ice houses, as well as episodes of greater heating, called hothouse events. In some scenarios, like what happened in the Paleo-Proterozoic 2.4 billion years ago, and in the Neo-Proterozoic about 700 million years ago, we were in a snowball Earth regime where climate change triggered cooling, growing polar ice caps reflected more light, cooling the Earth even further, and a snowball Earth could result. But a hothouse can be triggered if you freeze the oceans over and volcanism continues pumping carbon dioxide in the atmosphere because it doesn't, Earth's interior doesn't care, doesn't respond so much to what's going on just at the surface, this thin layer at the surface. So that CO2 can build up and build up until the whole system goes to a catastrophic melting event, and you have an ultra greenhouse. So you can have an ultra greenhouse, a hot house. You have massive CO2 cycling that gets restarted, but then it draws down CO2 in the atmosphere, and you plunge back into a cold region, again, an ice house. So these huge climate swings tend to coincide with major evolutionary changes in biology. And we're still working on trying to understand that. So the last word on the greenhouse effect. What are we doing? The amount of carbon dioxide that's been pumped into the atmosphere just from the last 50 or 60 years or so of direct measurements of air has increased dramatically. Earth's average surface temperature has risen more than half a degree during this time. My old professor, Dave Keeling, whose office was right across the hall from me at the Scripps Institution of Oceanography, he started these measurements in the 50s, and he reported this famous curve called the Keeling curve, which shows a rise in carbon dioxide in the atmosphere. This is not exclusively from volcanism. It's not natural cycling, because this carbon dioxide is different. It is isotopically light in exactly the kind of isotopic signature that we expect from burning fossil fuels. It also correlates with other measures of increase in industrial activity. And this coincides with the rise in human population. So we are changing the climate dramatically. There is no question of the role of humans in changing climate, thanks to pumping all of this old organic matter unnaturally back into the atmosphere. So it's probable that we're causing climate change and global warming. Do you think that this is a problem? Here, our models and observations match for changes thanks to increase in industrial activity, especially since the Industrial Revolution in the late 19th century. In your opinion, is human-induced climate change really happening? Write in the comments box. Be part of the conversation. And that concludes day 1 of our Earth and Space Sciences tutorials. And don't forget to subscribe. Hit that subscribe button. Join our community. Visit creo.space. And I shall see you next time.